Hi viewers, this is Dr. Jana and you are watching video with me, and in this video today we will be covering on these genetic algorithms, especially who are working for this genetic algorithm based algorithm for finding optimal solutions. So this video is the right video for them. See, this genetic algorithm, it is a search based optimization techniques. Okay, from the main name, and it is based on the principle of genetics as well as the natural selection. So it is used to find the optimal solution. The optimal solution means out of a pool of solution, what is the best solution? We call it as the optimal solutions. Or in the other word, optimization is the process of making something better, or which one is the better one. So that is the main aim of going for this genetic algorithm based search. So now I can say the genetic algorithm, this is a search based algorithm and it is based on the concept of natural selection and genetics, right? So these genetic algorithms are a subset of evolutionary concept. So if you remember the Darwin's evolution theory, so this is also based on the same thing, that is survival is the fittest, that is the condition here. So now in genetic algorithms we have a pool of population. What is this population? Because naturally we are taking population. Here this population is possible solutions to the given problem. Because remember one thing, we are not in optimization, we are not going to get a solution to a problem. For a problem there is a number of solutions given, and in the optimizations we have to find the best solution. Remember always, optimization is never going to give a solution, but out of a possible group of solutions or possible population of solutions, I am going to find the best solution. So these solutions undergo recombinations and mutations, okay, producing new children, and the process is repeated over various generations. So this is the main principle what we are going to adapt it here. Fine. And each individual is assigned a fitness value based on the objective function value, and the fitter individuals are given a higher chance to mate and yield more fitter individuals. So this is the Darwin's theory, survival is the fittest. Fine. Then let us have a look what is happening here. Now suppose we have in a given problem space, we take a population, that is the small set of chromosomes, we can take it here. Suppose the population space is the entire thing is there, the your problem thing given, right? From this you can see the matrix like things it you are doing. So this I call it the population, the entire thing, the number of rows and column, it is a population. And this population, it is a subset of all the possible solutions to the given problem. For a given problem, suppose like this, another 10-15 sets are there. So out of that I take one, the entire rows and columns, you can see in the green color I have written, this is the population set of chromosomes, right? And this population for a genetic algorithm, it is analog to the populations for human being, except that instead of human beings, here we are taking the candidate solutions, right? Here we are taking the candidate solution, that means out of number of solutions we are selecting some solutions. This is representing the human beings. Now you see, if the entire, if you see a tabular form it is given, if entire take is population, one row of data you can see it here. This we call as a chromosome. So I can explain you like this, a chromosome is one such solution to the given problem. So for the entire problem, if this is the population of that one, then this one row, what we called as the chromosome, this is only one solution, okay? So one such solution to the given problem. Now what is the gene? So out of this chromosome, suppose I select one cell only here, this I call it the gene. And inside the gene, what is the value? So you can see what is the chromosome here. No, 0, 1, 0, 1, 0, 1, 0, 1, this is the chromosome. Out of that I am selecting only this cell, the entire cell I call it as a gene. And inside the gene some value is there. What is the value? Value is equal to given 0, somewhere 1, this is called the allele, okay? So these are the very fundamental notations we are using in our genetic algorithm. So coming to the next slide, we sometimes confuse about the genotype and phenotype. See, there are two things you see, remember. One is the actual solution space. What is there in the natural things? What is the actual solution space? But actual solution space, what we have to do? So we have to bring it to a computer space. That means we have to first model it. So for that, what do we do? This, what is there in the actual solution space, we call it as the phenotype space. And what we bring to the computational space, that we call the genotype. Remember, so actual space, actual solution space, it is the phenotype, and the computational space we call it as the genotype. Now, then how do we convert this actual solution space to the computational or the computation space? It is by the encoding. So encoding is a technique by which the actual solution space is converted to computation space, or phenotype space is converted to genotype. The reverse process is there. We are going for the decoding. In the decoding, we are converting the computation space into the actual solution space, or genotype to the phenotype. The same thing it is given here. Genotype is a population in the computation space. What is genotype? Genotype here, it is in the computation space. Okay. In this computational process, in this computation space, the solution are represented by a way which can be easily understood, and the machine also can understand all things. 0, 1, 0, 1 binary things it is represented, right? So what is phenotype? Phenotype is the population in the actual real world solution. In the real world problem, what is the solutions? They are represented by the phenotype. Okay? Solution represented in a way that is represented the real world situation. The real world situation the computer cannot understand. So it is to encoded so that it is converted to a format which the computer can understand. So this is the process. We call it the encoding from real time to the computational space, and decoding from computational space to the real world. All the things this is taken care, right? Then in our next slide, we are going for finding the fitness function. See, if you remember the Darwin's theory, so-called Darwin's theory, so we call it as the survival is the fittest. If you remember here that I have given you on the first, second slide. Okay, this is the slide number 4. If you remember here, we have the famous Darwin's theory, survival of the fittest. Survival of the only the fittest people, they only survive. Remaining people they die in the course of time by fighting, by natural calamity, whatever things they die, right? So now, now how do we find this fitness function? Because that fitness is different thing. Who are tolerant, who can fight, and who can stay, that is different thing. Here, how do we find the fitness function? What is the fitness function? Let us know. A fitness function, simply defined, it is a function which takes the solution as input, because so many solutions we are having in the population. So it takes the solution as input and produces the suitability of that solution as the output, whether that solution is suitable, because out of a number of solutions, which one is the best solution, that you have to select based on this fitness. Now, for this, we go for a number of genetic operators. What are the operators? Because the main aim is here to produce some offspring, okay, to produce some offspring. How do we produce? So by altering the genetic composition, we can find some good children. Okay, so naturally what happens? A boy from a good background, marry a girl from the good background, so physical fitness should be there, and they should be disease free, they should be this, that, and all things. So then maybe we are expecting a good child will come. The same thing also it is applied here. So these includes crossover, mutations, and selection. Okay. Then first of all things, we need to represent what are the chromosomes we are telling. First of all, we have to represent all the things. Without representing, how to work on these computer systems? So we have a number of representations, or they call it the genotype representations, or the first thing is the binary representations. Some problem we can represent it by binary number, by the Boolean decision variables like 0, 0, 1, 0, 1, 1, all things we can represent. Okay. So for some problems, on the solution space consists of Boolean decision variables, yes or no. So this is represented by the yes is represented by 1 and no is represented by 0. So we can convert this yes no to this binary representations, and we can represent by 0 or 1. Then is the integer representation. Suppose sometimes I want to going to take the decision based on the different directions like north, east, south, west, all things are there. So how shall I represent this type of things in binary? What is the meaning of binary? 0 is north or south? 1 is east or west, because that is difficult to represent here. So there we are going for the integer representation. Say for example, I can represent 0 for east direction, or I can say 0 for north direction, 1 for south direction, and 2 for east direction, and 3 for west directions. Now, so based on this, we can select the integers between 0 to 3 or 1 to 4, whatever the things. Here it is taken 1 to 4. Okay, then you can start. North is equal to 1, south is equal to 2, east is equal to 3, and west is equal to 4. So those things, instead of it cannot be represented as a binary number, so I am representing by the integers, right? So this is the thing, it is explained here. Then coming to the next type of things, so we call it the permutation representations, where you use, suppose I am going for the traveling salesman problem, that I want to find out of the solutions, because any route you can go, finally you can reach there, but the thing is that it takes long time or long distance you have to travel, and you may travel some places several times. But all of you know the traveling salesman problem. So it has to tour of all the cities and visiting each city exactly one time and come back to the started city. That means the city where you started, you have to come back. That only you are visiting 2 times. Otherwise, all the city you are traveling only one time, and the total distance of the tour has to be minimized. So that means traveling only the minimum distance we are going to cover, because the salesman they have to cover, and see again and again they are repeating, because it is a time factor and as well as the expenditure of money. So in that case, so they plan it. And this type of problem, suppose I want to using the genetic algorithm, I want to represent. So in that case, some A to B distance is 1 kilometer, so B to C 5 kilometer, some C to E 9 kilometer. So or like that it is there. So these things are represented using this permutation representation. It is clear? Then here population is a subset of the solutions in the current generation, and it can also be defined as a set of chromosomes. So you can see it is just like a chromosome, I am writing it here. Then how do we go for the population initialization? There are 2 primary methods to initialize a population in the genetic algorithm. How do we initialize? One is the random initialization, second one is the heuristic initializations. Random initializations, you can clearly understand, populations or populate the initial populations with completely random solutions. Any randomly, some here, there, anywhere you can take it randomly. But in case of heuristic initializations, populate the initial populations using some known heuristic. Okay, based on some principle, based on certain things, we are going to find the heuristic initialization. So these are the 2 type of population initialization problem we apply. So then we are going to our next slide, where we are going to find the fitness function. Here they are going to use the famous knapsack. This fitness function simply defined as a function which takes a candidate solutions to the problem as input and produces as output how fit it can. So suppose some item numbers are there, 0, 1, 2, 3, 4, 5, 6 is there, and some chromosomes are represented as 0, 1, 0, 1, like that is there, and the profit value they are represented as 2, 9, whatever the profit value. Okay, then the weight value also it is given here. Now the we have to always define a capacity of this knapsack. Suppose the knapsack capacity is equal to 15, and the total associated profit, say it is equal to 18. Now you see it here. So if you go for this profit value 2 plus 9, 11, like that, or whatever things are there. So the last item, it is not picked as it exceeds the, because we always count that it does not exceed 15, because that is the limit given. So based on that, what are the things beyond that 15, that only we are going to consider. So this is the thing. I think we will explain all the things in this knapsack. Another video will make it here. Then we go for how do we go for this fitness population selections, on what is the principle we go for these things. Now the fitness proportionate selection is one of the most popular way of pattern selection or the parent selections. Okay, so in this every individual can become a parent with a probability which is proportional to the fitness. So if the person is fit, then he can be parent, he can marry and he can produce children. Therefore, fitter individuals have a higher chance of mating. Suppose somebody is suffering with cancer, somebody is suffering with TB, he is not suitable. They usually would avoid this marriage and all, because the children will be sick and all things. So here that we decide based on this fitness function. Okay. So who are the fitter individual? They have higher chance of mating and propagating their features to the next generation. Now consider in this what we are considering, we are taking a circular wheel. You can see it is just like a pie, n number of pies are there. This blue color is one, this red color is one, again this grey color is there, yellow color is there, deep blue color there, and green color, all these are there. How do you calculate all the things? Suppose they are represented by the chromosome A. So A is equal to the fitness is equal to given something 8.2. B, how it is calculated like this? Whatever the values here, the fitness, you calculate the total thing. Okay. So 8.2 plus 3.2 plus 1.4 plus 1.2, all these things. So 8.2 divided by the total, so that percentage it is represented here. Similarly, 3.2 divided by the total, B proportionate, it is given here. C is given here. So A, B, C, D, E, F, all this value we can get it like this. Are you getting me? So each individual get a proportion of the circle which is proportional to the fitness value. Okay. So based on this we are doing. But what is the principle here? So we are using a single point. So there are so many methods to select all the things in the single point. Then we are going for just rotating this wheel. Okay. So once you go for this thing, then there is a chance, because which has the highest percentage, they have more chance getting selected. But we done it here, and suppose we find this color, yellow color. Okay. That is A, B, C, D. So D was selected here. You get it now? So now the same thing it is going to see. It is clear that a fitter individual has a greater pi on the wheel, and is therefore it has a greater chance of landing in front of this fixed point. What is the fixed point? The fixed point, one point we have taken it here. This is the fixed point. So just to give a rotation to this wheel, so which one it will be appearing in front of that one? We say, because generally, because this you see the chromosome A, because the percentage is around 48%, just less than 50%, so it has more chance. Okay, but it is not necessary that all the time it will come. So anything it can come here. So what are the shade of the pi portion? It is coming in front of the wheel. The wheel is pointing, so that is selected here. Okay, so this is the thing. So same principle is there here. Now, how the implementation calculate S, that is the sum of the fitness. The fitness 8.2 I given, then generate a random number between 0 and S. Suppose S is equal to something 18, we select a random number and start from the top of the populations, keep adding this fitness to the partial sum P. Okay, so this P should be less than S. S is randomly we have taken the sum of the fitness function S. Okay, S is the sum of the fitness function, it is S. So P we have taken, it is starting from the top of the populations. We keep on adding. First is 8, 8 plus 3 is equal to 11, 11 plus 2 like that. And where you see when P is less than S, the individual for which P exceeds S is the chosen individuals. Are you getting? So this is the principle. On this we are going to go for the selections right here. Then I am going for the stochastic universal sampling or SUS. Okay. Here if you remember the previous one and this one, there is only a single fixed point, but here we are putting two fixed points. Here this side one, this side also one. See, the stochastic universal sampling is quite similar to the roulette wheel selection. The previous one what we studied, that is the roulette wheel selection. However, instead of having just one fixed point, we have multiple fixed points as shown in the following images. Therefore, all the parents are chosen in just one spin. So we are giving one spin. So what are the parents? Two parents we are selecting here. Okay, chosen in just one spin of the wheel. Also, such a step encourages the highly fit individuals to be chosen at least once. So all are given a chance here. So it is to be noted that the fitness proportionate selection method don't work for cases where the fitness can take a negative value. If the fitness has a negative value, so it won't take that one here. Okay, that is the only thing you have to remember. Okay. So then we are moving to our next slide, where we are going for another way is also the tournament selections. In the tournament selections, we conduct a tournament of football match, conduct a tournament of cricket match. We say it like this. So suppose in K ways tournament is selected. So A, B, C, D like that. You are giving this 1, 2, 3, 4 like that. So in K ways tournament selections, we select K individual. Suppose here K is equal to 3. I select A individual. I select E. I select T. Whom I selected? I selected A. I selected E, I select T. So in a tournament, because in the tournament, suppose you are having 10 departments, so 4 departments go for the playing match between A and B, C and D, and A, B, C, D. What is the result? You keep it there. Then G, H, A, K, L, M, N, like that, because you are having 5 set, 5 into 10 number of departments are there. So out of these 5, 5 winners will be there. So again we make a tournament among these 5. So in the 5, suppose 3, 5, 7 were the winners that time. So 1 versus 3, 3 versus 5, 2 versus 7, like that you go for. Then finally we go for the semi-final. So here also the same thing, but here A, E and T have selected, but they have their individual fitness value. What is the fitness value of A? You can see the left hand side, the fitness is 5. What is the fitness of E? It is 2. What is the fitness of T? It is 2. So 2 to 5, what is the highest fitness? Highest fitness is 5. So we pick the parent of highest fitness. Okay, get it now? The tournament selection is also extremely proportional in literature, as it can even work with negative fitness also we can work here. Fine. So this is the thing, some of the selections. Then another is the rank selection. So why? Because so many selection is there, why we go for this rank selection? The rank selection also work with negative fitness. The previous one work with the tournament, work with the negative fitness. Rank selections also work with the negative fitness values. And it is mostly used when the individuals in the populations have very close fitness. Say previously 8 is there, 1 is there. Here you see all are nearer. 1 is 8.1, 1 is 8.0, 1 is 8.05. All are very close to each other. So you see minimum is the 7.95 and maximum is the, it is very less difference is there. Okay. So in these cases we can go for the rank selection. Okay. So what you do here, fitness is not important out of this fitness, because all are fit, because when all are 7, between 7 and 8 all are fit. But according to what is the rank? So what is the highest rank? 8.1. Which is the highest fitness? They are the rank 1. The next one 8.05 is the next highest. 8.02 the next height, like that. Okay. 8.1, next is 8.05, next is 8.02, next is 8.0, next is 7.99, and the last one is 7.95. You got it now? Now this leads to each individual having an almost equal share all of the pie. So you can see, if you look here you cannot understand which one is more and which one is less. So all are looking equal, as shown in the following images, and hence each individuals, no matter how fit relative to each other, has an approximately same probability of getting selected as a parent, and this in turn leads to a loss in the selection pressure towards their individuals, so making the genetic algorithm make poor parent selections as a solution. So in that case what we do, what I told you, that the rank is more important than the fitness here. Great. Now if you see in this, we remove the concept of the fitness value, but we go for the rank. As I told you that 8.1 is the highest rank, then 8.05 is the second highest rank, 8.02 is the third rank, like that I already given a rank. And now the individuals having the higher rank, they are given the priority first. Okay. These higher ranked individuals are preferred more than the low ranked ones. Clear? So this is the thing, you can take it here. So now we are going for the crossovers. Because first is the selection, you selected somebody, then we are going to crossover. What we do? See, we select a boy from one village or one group of people, and we select a girl from another village. They may have the fitness, they must have a good birth, they may have a good education, they may have the good things, living standard, they may have the good cleanliness and all things. So then we go for the, we fix the marriage, especially the ideally the arranged marriage, what is done in India, some part of these people, they do it here, arranged marriage. So that is the main purpose of that one. Okay, then how do we go for the crossover, and what are the different type of crossovers? Crossovers means we are exchanging all this data here. See, I go for 1 point crossover. In 1 point crossover, can you see I am selecting 1 point here, the red color here. Okay. In this 1 point crossover, a random crossover point is selected and the tails of its two parents are swapped. What is this is the tail means this is the right hand side. You get it now? So what is your 5, 6, 7, 8, 9? What is your 3, 5, 7? This is the head part and this is the tail part. Okay. The tail of two, this is chromosome A and this is chromosome B. So A and B tail pass, they are swapped. That means 3, 5, 7, 5, 8. 3, 5, 7, 5, 8 is swapped here and 5, 6, 7, 8, 9 it is brought to the bottom. Okay. This is one, we call it the 1 point crossovers. Okay. So then we are going for the multi-point crossover. That here we are selecting only 1 point randomly, but I am selecting 2 points. I am selecting 1 point here. I am selecting 1 point here. So what are the value of these chromosomes between these 2 points that I swap? That means 4, 2, 3 come here and the 3, 4, 5 come here. You get it now? So this I called the multi-point crossover. Getting me? Then I am going for the uniform crossover, because so there in the previous cases we are selecting some points, either a single point or multi-point, all the things. I am not doing that one. In a uniform crossover, we don't divide the chromosome into segments. There we are dividing into segment and we are swapping. Rather, we treat each gene separately. So in this, we essentially just you go for tossing a coin. Suppose case 0. 0 and 5 is there. I toss a coin. If it is head, then I swap 5 and 0. 5 comes here, 0 comes here. Can you see it here? But second 1, 8. I toss the coin, it is tail. So I leave it as it is. Third one 2, 9. I toss the coin, suppose it is head. Again so it is based on the toss of the coin. If it is head, I am changing. If it is tail, I am leaving. Okay. So this is one of the crossover. We call it the uniform crossover. Most probably we follow this uniform crossover also. Then we go for the mutation. Okay. Till now we studied about what is the selection. Then we studied about the crossover, and finally we are going for this mutation. So mutation is the part of this genetic algorithm which is related to the exploration. That means out of this existing, if you repeat it again and again, we call that the that is called the exploitation out of the existing. So you are trying to get something new, that we call the exploration out of the set of the receivable. It has been observed that mutation is essential to the convergence of the genetic algorithm. So here I am going for bit flip mutation. Bit flip mutation. In this bit flip mutation, we select one or more random bits and flip them. Flip means what is the value, we change it here, because all are suppose I selected 1. Then and here this is 0, 1, 2, 3. Here it is there. This third value, instead of 1, you just change it to 0. If 1 is there, change it to 0. 0 is there, just randomly select here. Suppose I selected here, what is the value? 1, I selected 0. Suppose I selected here 0, it was 0, I convert to 1, like that. Then the random resetting. Okay. In the random resetting, this is an extension of this bit flip for the integer representations. In this, a random value from the set of permissible values is assigned to a randomly chosen genes. So I select here, I select here, I select here, and those values are only flips. Okay, or we go for the change, right? So these are about the different mutations. Another is the swap mutations. In the swap mutations, what you do? Suppose in a chromosome, you can see here, I selected 2 and 6. The value of these things, this is a number system representation, integer system. So 6 and 2 I swap. That means instead of 2 I put it 6, instead of 6 I put this 2. This is the swap. Then the scramble mutations. Okay, that is we are interchanging the value here in the swap. In the scramble mutation, the scramble mutation is also popular with the permutations type. What we do it here? In this form, the entire chromosomes of a subset of a gene is chosen and their values are scrambled. Scrambled means not in order. Say 2, 3, 4, 5, 6. This is the thing I selected. So I can put 3 here, I can put 5 here, I can put 4 here, anything I can put here. I put 3 here first, then I put 6 here, because all the things I am putting, but randomly I am putting it here. It is not in order. Then inverse mutation, this is another way also. Suppose I select between 2 and 6 in this chromosome. Then what I do? Then 6 come first, then 5 come second, then 4 come, then 3 come, 2 come. This is just the inverse mutations. So these are some of the different mutations we follow. Then how do we go for the survivor selections? The survivor selection policy, it determines which individuals are to be kicked out and which are to be kept for the next generations. Say some people are diseased, some people are suffering from, we don't encourage them for marriage and have children. Okay, so it is a crucial as it should ensure that the fitter individuals are not kicked out, who are physical fit. So if you remove them, then it is a lost populations. While at the same time, diversity should be maintained. Different type of people, because diversity means we are taking randomly this one, not that only from one area. Some genetic algorithms employ elitism. So in simple terms, it means the current fitness member of the population is always propagated to the next generation. Therefore, under no circumstances can the fitness member of the current populations be replaced. Okay, so we should not miss one fit candidate here. Then another is the age-based selections. See, sometimes I take an example, you don't misunderstand me. Suppose I am selecting a couple. Can I select a couple with age more than 60? Even if they are physical fit, they are doing exercise, there is no disease. But age is a factor, so age is 60. So in that case, in age-based selections, we don't have a notion of fitness. Even if you are fit, it is based on the premise that each individual is allowed in the populations for a finite generation where it is allowed to reproduce. That means we have a age limit, say up to 40 years, say like that. We allow some people to marry. After 60, 70, what is the meaning of that? Okay, get it now? So that means based on this age, people is allowed to here produce, and based on the age, they are kicked out of this population, no matter how good or how fit they are. Okay, so these are some of the things we remember. Then we see here, suppose we go for this tank, you can check it here. Now, here I am maintaining one is the age, second one is the fitness value, third is the chromosome. I selected this P4 chromosome, I also selected this P7 chromosome. For P4, what is the age factor? It is 10. For P7, that is, they are already in the last, because it is just a mapping. I am not telling because for 10-year boy is allowed for mating or 6, it is not like that. So let be 6 for 60, 8 for 80, 5 for 50, 10 for 100 and 9 for 90. So can you allow somebody at the age of 100 or 90 to marry? No. So what we do? So we make them out of this group, right? Then what I do? So this I replace by another chromosome C1 with fitness value 0.8 and C2 with fitness value something. Okay, that means what I do? So this value, you get it now? So now this is only I am taking the fitness value, and the age is less. It is not around 10 and it may be 1 or 2. Now here the age is 0 taken. You get, because initially I am putting it here in this group, the age is 0, and here 8 fitness, and it is the C1. Are you getting me? So this P4 is replaced by C1. See, P4 is not there because the age is 10 already. Now the new age becomes 0 and the fitness is 8. Here the fitness is 9 and age becomes 0 for this C2. This is also one of the way we go using that one. Okay. Then the fitness based selection. So in this fitness based selection, the children tend to replace the least fit individuals in the populations. Okay. Are you getting now? Then the selection of these least fit individuals may be done using a variations of any of the selection policies described below. You can go for the tournament selection, you can go for the fitness proportion selection. Based on that we select. Say for example, suppose the chromosome you see P1 and P9. P1 what is the fitness? It is 1. P9 what is the fitness? It is 1. Are you getting me? Are you getting me? So now what I am going to? I am going to replace with values C1 and C2. C1 has a fitness 8. Sorry, not P9. I am selecting P10. Here it is 0. Okay. So C1 having a fitness value 8 and C2 is having a fitness 9. Right. That P1 is replaced by C1 with fitness value 8 and P10 is replaced by C2 with the fitness value 9. So this is also another way. It is purely based on this fitness. Okay. Finally, we are going for the termination conditions, and where there has been no improvement in the populations for X iterations, then we have to terminate this condition. Because why we are doing? Because we are going for this all these things for the betterment, because after certain iterations there is no improvement, then we can stop it. And when you reach an absolute number of generations, so we have gone for a number of 50, 100 generation, after that how many generations? It is stopped. Okay, when the objective function value has reached a certain predefined value, because sometimes we fix the objective function value, when you reach that value you have to you have to go for this termination condition of the genetic algorithm. Then what are the applications? Say we have a lot of applications where you can use this. First one is the optimizations. Any type of optimization we can use the genetic algorithm. The neural networks also we can use this thing, genetic algorithm. For image processing also we can use this genetic algorithm. For machine learning, from robot trajectory generation, for DNA analysis, traveling salesman problem and its applications. These are the important areas where we can apply this genetic algorithm. Hope you understand the basic concepts. If you have any query, please do send SMS or mail to me. I will try to answer your questions. And if you really like this video, please do share with your friends and don't forget to subscribe. Please take care of health. In our next part of the video, we will giving the complete coding for a case study, how to use this genetic algorithm in Python to solve some real-time problem. Thank you for watching this video. Have a good day. Thank you.